this is section 2.2, and we're going to learn two rules. One's called the first derivative rule, and the other's called the second derivative rule. The first derivative rule says that the sign, the positive or negativeness of your first derivative, tells you whether the graph is increasing or decreasing. If your first derivative is positive for a certain x value, your graph is increasing at that x value. And if it's negative, your graph is decreasing at that x value. So information is going to be put into categories now. Information from the function is going to give us location. Information from the first derivative, so any of these pieces of information, give us direction of our curve. And we want to keep them straight. So when we see a statement like f of 3 is 4, that tells us there's a point on the graph where when you plug in 3, you get out 4. So that information leads us to that point, 3, 4. This information about the derivative is not giving us location. It's telling us how the graph is moving. So this is saying that the graph is increasing. Here the graph is decreasing. And at this point, the graph is not increasing or decreasing. The graph is steady. It usually means it's turning in some way. So not always, but usually it's going to mean it's turning. So what I mean by that is we don't know how, but we know the graph has this kind of a direction when we use numbers less than 3 and plug it in. And we know that when we use numbers greater than 3 and plug it into the function, it has this kind of a direction. So like a roller coaster going up and then a roller coaster coming down. But right at that point of 3, we have a horizontal asymptote. So at that point, the slopes of the tangent aren't positive or negative, they're 0. And it's a place in the graph where we wouldn't call it increasing or decreasing. And in fact, we learned last time we're going to call it a relative max, that change in direction in our curve. So how it's increasing or decreasing, like I said, we don't necessarily know what this looks like. You know, there's a lot of different ways that we could draw increasing. Even like that, we could draw increasing. So we're going to need a little bit more information in order to know how something's increasing. And that has to do with the second derivative rule. It tells us about concavity. So this second derivative gives us yet another piece of information about what's going on when x is a, when it takes on the value 3 or 4 or 10. This greater than 0 would tell us that the graph is concave up. Less than 0 in our second derivative will tell us the graph is concave down. And so in terms of a picture, if both the first and the second derivative were positive at a value a, it would not only be increasing, but it would be doing it in a way that it was concave up or it would hold water. If the first derivative was positive and the second was negative, then our graph would be increasing, but it would be doing it in a way that it would not hold water. It would shed water. It's concave down. A negative first derivative would be decreasing, so both of these are decreasing, but in different ways, because a positive second derivative would tell us it's doing in a way that it's concave up, as opposed to concave down. So knowing both of those pieces of information helps us decide how we're going to draw increasing or decreasing. So if we look at the next page, the information here is, we're going to use it all to draw a picture, but it's broken into pieces because Each of these tells us different information that we need. These statements about function values are giving us location. So a place to anchor our graph, a place that we know our graph exists. That when I plug 2 in, I get 3 out. When I plug 4 in, I get 6 out. And when I plug 6 in, I get 7 out. Those are anchors for our graph. The graph has to go through those points. And when I plug an X value in, a Y value comes out. This is direction information because it's coming out of the first derivative. But all it says about direction is it's not increasing or decreasing. That's what the 0 means. So it's not a lot of information about direction saying that it's not increasing or decreasing. But what we're going to think is probably that's where the graph turns around because there's a horizontal tangent there. That's what the 0 means. And the third piece of information tells us about concavity because it's coming from the second derivative. So greater than 0 means concave up, and less than 0 means concave down. And equal to 0 means an inflection point. So if we put all this information together, we know that for values of x that are less than 4, so for this whole part of the graph, it's concave down. And for this whole part, greater than 4, it's concave up. And in between, it's not concave up or down. And if we think our graph is turning around when x is 2, we could imagine what concave up and turning around would look like right there at that point. And if we think it's turning around again when x is 6, but it's concave down when it's doing that, we could imagine that it has that general shape. So here would be an inflection point, here would be a relative max, and here would be a relative min. And that's a graph that satisfies those conditions. It's not the only graph that satisfies them, but any graph would have to go through these 3 points with that kind of a direction and a concavity. If we're trying to find that inflection point, we now know how to do it. We want to know where is the second derivative equal to 0. Now, there'll also be times where inflection happens where the second derivative is undefined. But this is a polynomial, and we know that when we take its derivative, we get another polynomial. And when we do it again, we get another polynomial. And polynomials are never undefined, never have any issue with their domain. So we're going to focus on where it's equal to 0. So we had a first derivative first. First derivative is x squared minus 8x plus 18. But we want to buzz right by that first derivative to the second derivative. Because the first derivative doesn't tell us anything about concavity. It's all about direction. And if I want an inflection point, I want the second derivative set equal to 0. So I'm going to be looking at the place where x equals 4. And I think that's where my inflection point's going to be. But I want to prove it. And in order to prove it, I want to think about the number line where my x values are on the horizontal x-axis. And I want to notice that that second derivative was 0 when x was 4. But I want to know what the second derivative was when x was 3 and when x was 5, so I can see whether I had a change in concavity or not. So if I plug 3 into the second derivative, I get a negative value out. And the fact that that was negative tells me my graph was concave down. But if I plug 5 into that second derivative, I get a positive value out. And so the graph was concave up on the other side of 0. On the other side, sorry, of the number 4, where the second derivative was 0. So I basically have just shown a change in concavity around that x value of 4. And that change in concavity is happening when x is 4 and when y is, now I got to plug 4 back into my function. So 4 cubed and 4 times 4 squared and 18 times 4 and 10. When I put all those numbers together, I'll let you do that. But that's my y value. So that is my inflection point. I set the second derivative equal to 0, solve for x, show a change in concavity, and then get the y value. And finally, if I look at this last picture, I want to make sure we go over this because it's a little confusing in the homework. This is a graph of f prime of x. It is not a graph of the function. But I can take this graph and I can use the information from this derivative to know something about my function. So if I want to know the slope of my function when x is 1, this derivative tells me. This derivative tells me when I plug 1 into it, I get 2 out. And that means the slope of my function when x is 1 is 2. So my function's got a pretty steep slope. I don't know where because I don't have a function value to give me a y value, but I know when I plug 1 into my function, it's increasing. How does my function change on the interval? This should be between 1 and 2. Sorry, that's a typo. How does my function change when x goes from 1 to 2? Well, if you look at this, you might be deceived in thinking that the function is decreasing. But the answer is it is still increasing. Because f prime of 1 is 2 and f prime of 2 is 1. The slope along that entire interval from 1 to 2 is positive. It's a positive slope. So my function is increasing on that entire interval. The thing is, it's just not increasing as fast. So it's increasing, it's got a slope of 2 here, and by the time it gets to 2, it only has a slope that's of 1. But either way, both of those derivatives are telling me my graph is increasing. It's just increasing at a slower rate than it was before. For what values does it have a horizontal tangent line? Well, that would be right here when x is 3, because the slope at 3 is 0, and that's a horizontal tangent line. So by the time I get to x equals 3, my graph has a horizontal tangent. And then after I get past 3, my slope is negative. So when I plug 4 in here, I get a negative slope. So if my function had a horizontal slope at 3, it had a positive slope before that, but it was getting less and less steep as we went, it could look like this, where I have a slope of 2 when x is 1, a slope of 1 when x is 2, horizontal, and then it starts being negative. And so I would call, there would be a relative max when x was 3 because of this information. The slope was positive but getting less positive and then getting negative. All this information is coming from my first derivative that helps me draw a picture of my function. I can't be exact about my picture because I don't have any function values themselves, but this is the direction, right? This is a slope of 2. This is a slope of 1. This is a slope of 0. This is a slope of -1. And so these values that I'm grabbing from this derivative are matching with the slopes of the tangents of my curve. So there's a problem like that to try in your homework. Just hopefully will help.